So I am going to tell you a little bit about my PhD work, which I did at Brandeis University under Jordan Pollock. And
would you be able to speak up?
Pardon me?
Would you be able to speak louder, a little harder?
Yeah, there's no door, huh? I'll try.
Thank you.
Yeah, just yell at me again if you can't hear. So I studied coevolutionary algorithms and an idea about changing the incentive structure and the evolving populations by adding this notion of informativeness. So I'll tell you about that. But first, maybe a little bit about coevolution. Daniel Hillis in 1990 produced a result that was very stimulating for the field. He was evolving these things called sorting networks, and the way that they work is you have some number of inputs, here 16, and numbers can shoot down these lines, and then there are these compare swap gates that can span some of the lines. And so if two numbers are going down these two lines and hit one of these gates, if they're out of order, they're swapped by the gate. And the problem here is arrange these things in such a way that no matter what input you put in, it always comes out in sorted order. And an additional problem is do that with a minimum number of these gates. So this is a circuit design problem that Donald Knuth and others have worked on, and there was sort of a debate about the minimal number of gates you would need and so on. And the best known at the time was, I believe, 60 for the 16 input one. And Hillis, in 1990, set up a coevolutionary algorithm to evolve these designs in a computer, and discovered this particular one that was 61 gates, so only one worse or one longer than the best known at the time. So it was a pretty remarkable result that this kind of algorithm could produce a circuit design quasi-automatically that was almost as good as what very good computer scientists could produce. Not too long later, we have another example, this time from a more artificial lighty perspective, of a coevolutionary algorithm being used to evolve these 3D physical creatures along with behaviors that battle for a cube. I don't know if y'all are familiar with this work, but it was also quite stimulating and gave a lot of food for thought to the field. So these two results were quite encouraging. They very nice outcomes were produced by coevolutionary algorithms, and so there's a lot of excitement about what these algorithms could do, which has spawned another 15-odd years of research. But I wanted to take a step backward in time for a minute and make a connection with some earlier machine learning kind of work. Here is a quote from Arthur Samuel, who's known for automatically discovering checkers players. And here is expressed, I think, the kind of hope that you might have for an algorithm like a coevolutionary algorithm, where just by using sort of raw computing power, you can minimize how much programming time human beings have to put into producing very good stuff. So from his perspective in 1959, he was saying, it's necessary to specify problem solutions in very minute detail. I would argue that hasn't changed a whole lot in the last nearly 50 years. But anyway, his dream there was that if we could get these machine learning methods just right, then maybe computers could produce wonderful stuff that we would have a hard time or nearly impossible time writing ourselves. And I'm making this connection with coevolutionary algorithms and Samuel's quote for a couple reasons. One of them is that this self-play procedure that he used is very much like a coevolutionary algorithm in the sense that you have these two entities that are interacting with one another, and then you modify the two different entities according to the outcome. And so the way that Samuel set this up is that there were two individuals, one called alpha, which was learning checkers, quote unquote, and then a second player, beta, which was being used as a test of alpha. And just as a cartoon, it works something like this. You would have these two checkers players, and you would have them interact. And the interaction is playing a game here.
What does coevolutionary mean?
Pardon me?
What does coevolutionary mean?
Okay, well, After I zip through this, I'm going to go through a cartoon primer on coevolutionary algorithms. So if you don't mind waiting a bit, we'll get to that. But the idea is just that it's an algorithm that mimics natural evolution, where you have multiple species that sort of interact with each other and impact each other's fitness. Sorry, I can't hear you.
I'm sorry, is it simply the fact that there's different entities with different starting initial states that makes it evolutionary, or is it the fact that we're dealing with multiple agents, so to speak, or is it as opposed to like, you know, a single agent evolving based on rules?
Yeah, so that's subject to debate, I suppose. But at least in, you know, there's the definition in biology. But I think in the consensus so far is that a system would be coevolutionary if you have at least two different roles or two different types of things. Whether they be in one population or many isn't so important. But as long as the entities playing one role have a direct impact on the entities playing the other role, then in the sense of which ones look good or not, then it qualifies as coevolutionary too. But getting back to Samuel here, he had these two guys. They interact with each other by playing a game of checkers, and there's some kind of outcome. So let's say in this case alpha wins. What happens next is that you make some modification to alpha, and Samuel had a crazy procedure for doing that, but you basically modify it, and you duplicate it, and it becomes the new beta. And then you iterate this, you continue. And he found checkers players in 1959 through 60 something that were roughly around human master level. But the important thing that I wanted to highlight about this is that his work differentiated two roles here. One of them would be a performing role. The alpha player is being incented, or you would like it, to perform well at the task. In other words, to play a good game of checkers. But the second role is more of an informative role. Here the beta player is being used as a test of alpha's capabilities. To see how good alpha is, you play a game against beta, and you're using that outcome to decide is alpha good or not. So really what beta is doing is informing about alpha. And this split in roles, as I said, it's a test. The split in roles is an important one that we'll see in a moment. See again many times in a moment. And this just kind of corroborates the idea that beta is being used as a test. Yeah?
Is the assumption that there is no evolution unless it's an improvement, or is it possible to improve better or worse? You know what I mean? For instance, any given iteration, I thrown alpha unless it's better.
In this algorithm, in Samuel's algorithm, the modified alpha replaces beta only when it's winning. But in the general algorithm, you could do whatever you like. You could do a selection or something like that, where you're not guaranteed to have.
No, there's ever-increasing skill here.
So, I have a few buts to raise. This beta player, since it's a frozen copy of alpha, was actually indirectly incented to be a performer. In other words, the alpha player is being incented to perform well, and beta is just a copy of that. So ultimately, the incentive for beta is to perform well as well. And the implicit belief behind this is that things that perform well also inform well. So if alpha is getting better, then the belief is that it's also telling you what other guys are good. But there's a question. Well, why not use a different procedure to try to find beta? Why just use a copy of alpha? Why not use some other mechanism which is more aligned with the idea of informing? And then there's a sort of meta but. Well, it works, so why? Why bother doing that?
Is there a but that alpha implicitly knows how beta thinks?
There's no knowledge, there's no explicit knowledge representation. It's
but it can anticipate because it has the same logic.
I suppose, but that's not built into how it plays. It's not looking at what it would do and then making an anticipation of what beta might do. It doesn't work that way.
Okay.
It's basically an evaluation function for a checkers player, so it doesn't have an explicit anticipation mechanism. So if anticipation happened, it would be implicitly maybe by accident.
Right.
Yeah. So why ask why? Well, in 1994, Susan Epstein had this article in Machine Learning where she explored this possibility of learning by self-play, but using other games like tic-tac-toe and loose tic-tac-toe and some others. And one of her observations there was that when you did self-play, in general, over most kind of games, it turns out that the players sort of lock themselves into a restricted number of paths through the game tree. So they don't widely explore the game tree. They actually, by playing one another, sort of only explore part of the game tree. And so whatever learning occurs is somehow isolated or over-specialized to just those paths through the game tree. Yeah?
Is that a function of the rules of the game? Is that because of like an emergent property of the rules of the game?
An emerging property of the game.
The rules of the game. Is there always selected certain outcomes? Do they prefer certain outcomes because of the game, or something inherent in the way that they're choosing, the algorithm choosing the fitness algorithm?
Well, that I guess is a bit of a debate too. But in deterministic games like tic-tac-toe, if your player is making deterministic choices, this is a very common problem. In a game like backgammon or some kind of randomized game, this isn't so much a problem at all. So it does depend on the structure of the game quite a lot.
More so the structure of the game.
Pardon?
More so the nature of the structure of the game, like the domain, the domain of index senses. So more so the rules.
I'm going to keep going. Yeah. So I'm going on with the ideal trainer idea. Basically, Epstein observed that this self-play procedure produces brittle strategies in quite a few games, including tic-tac-toe and some others. So her proposal in this paper was this idea of an ideal trainer, which is to train one player, like the alpha player, produce some kind of spectrum or varied number of opponents, and train against those. And the idea being to thoroughly test the capabilities of those other of the alpha player. So instead of just playing against one other thing, which might be a copy of itself, try to produce some kind of spectrum of opponents. And again, I wanted to just emphasize that her approach also differentiates these roles of performing and informing, but in her case, she treats them asymmetrically. So after that little introduction, I want to do a very quick primer on evolutionary algorithms to try to make the connection between what I just said and evolving stuff. So in a typical evolutionary algorithm, you have this thing called an objective function. And it maps some set of objects to the reals so that for any object in here, you can run it through the function and get a value for it. And this is thought of by analogy as the fitness of that thing. So if these are birds, maybe that gives how many offspring the bird has. But if these are tic-tac-toe strategies, this gives some kind of measurement of how good the strategy is. And then the algorithm maintains a population of elements from G, so some set of these things. I'm going to call them candidate solutions. And then there's a loop. You vary the members of the population, so that's like mutation in nature. You evaluate them all using this function to get their fitness, and then you apply some kind of selection operator that promotes the things with the higher fitness and somehow demotes the ones with the lower fitness, so that it starts to prefer the ones with the higher fitness. And there are a million ways to do all these different things. There's genetic programming, there's bit strings, there's evolution strategies, there's a wide variety of them, but they all kind of share this structure in common. And just as a cartoon, here's the same thing. So here's your population of things, and you produce some variants of those. So this guy gets a little mutant here and so on. And then you evaluate, so each of these things is run through the fitness function and gets a numerical value. And then you do some kind of selection, which in this case just removes the lowest fitness guys. Yeah? So selection removes the lowest fitness guys. And if it all works well, then you make some variants of these, and they have higher fitness, and you repeat, and pretty soon you've found wonderful things. The difference with a coevolutionary algorithm is that you don't have a function of this form. You don't have a function that can take one thing and spit out a number for you. Instead, the idea is that you interact things with one another. And you have these functions, which I'm writing like this, and this is the gratuitous math part of the talk, where S and T are two different kinds of things, two roles, so hence the co and coevolution. And if you have two of them, that you interact with one another, and you get some kind of value that's given here to the S guy or here to the T guy. So for example, these might be checkers players, and they play a game of checkers, and then the first guy wins, so he gets the value, and the second guy loses, so he gets a different value. That's all that's being said right here. Oh yeah.
If they're both getting better, wouldn't the scores sort of more or less remain similar through multiple evolutions?
Well, this isn't saying anything about how the scores are varying. Just this is a structure that you have to have. If you define a game like checkers, you're scoping out a space of players, which would be S, who play first, let's say, and another space of players T, who play second, and then this function would say, this guy plays with game with this guy, and we give some number to this guy. That's all this is saying. It's not saying anything about the dynamics.
Okay.
Like I said, this is a gratuitous math, so we won't say any more. So as a cartoon, here's how it goes. We have some population of guys over here, and we have some population of guys over here. So these might be checkers players, and these might be checkers players. And let's say we want to evaluate that guy. We pick some number of interactants for it, and we have them interact with each other, and there's some kind of number associated with it. So checkers won't give you a number, but this could be any kind of interaction at all, and there's some kind of number associated with it. And then we aggregate that somehow. So here I've just taken the average over these different interactions and given this a number 4. So this should remind you of the fitness function that you saw before, in the sense that you're getting a number now. And so you repeat that for other guys. You pick some interactants, you have them interact, and this guy gets a number. You do that for everybody. And now it looks like an ordinary evolutionary algorithm. Everybody gets a number, you can do selection and variation and so on. But note that the difference is that these numbers came from interacting with these and not from some single function. And so a few remarks here. To evaluate a guy, it interacted with a whole bunch of other guys, but the outcomes of all those interactions has been reduced to some kind of common numerical currency. Everybody's given a numerical fitness value. These guys in S are incented to perform well according to this function PS, whatever that is. And the entities in T might be incented to perform well according to this function P sub T. So for example, if this is saying give S a 1 if it wins, this might say give its opponent a -1 because it lost. But in any case, there's still some kind of performance criteria going on. And the question raised earlier about the distinction in roles between performing and informing arises again. Why not use some different procedure to incent individuals to perform? Because here we're seeking information. And another question, well, why not just use performance? If it works, who cares? And the problem is that it doesn't work. Since the 94 paper I mentioned about Carl Sims's co-evolving creatures, there's been at least a decade of work on applying coevolutionary algorithms of various kinds to all sorts of problems. And the unfortunate reality is that most of the time it doesn't work very well. In spite of the kind of stunning results of the early 90s that inspired the field, there's a whole order of magnitude longer list of negative results that sort of isolate and detail these various problems that can arise in coevolutionary algorithms and lead to suboptimal or confusing results. So they all have funny names, and I'm not going to go through all of them. But in short, the problem is that if you just sort of naively apply a coevolutionary algorithm to your favorite problem, the expectation is it's probably not going to work very well. And the response to these observations has been a large pile of specific remedies for each one. So as many observations of these problems as there have been at least as many remedies for each one of them. All kinds of hacks and techniques and methods to try to get around them. But in my mind, when I was starting my PhD work, I wondered about this question. Could all of that stuff, all of these issues that people have been battling for a decade or so, arise from a common problem, which is this reduction to common currency, this use of a single numerical value to aggregate the outcomes of many different interactions? That was my question. And if so, what could you do instead? And so here I'm gonna sort of outline what I came up with and try to make it sound plausible. A plausible thing you could do differently that alleviates some of the. So just to summarize what was said before, the idea was to evaluate one of these guys, you had to interact with some things, and then you summarize the outcomes somehow, like by averaging them, so that they got numerical fitness. But a different thing but the idea here is that in some sense you're comparing apples and oranges. Here it's obvious because this guy is interacting with a different subset of things than this one. As obvious as that may seem, there are algorithms that do that. But also, another thing that you might do is in order to compare this red guy and green guy, why not have them both interact against the same opponent and just compare how they do against those things? So in this case, against this particular opponent, red does worse than green. Now if we add some other opponent to the mix, this one, perhaps we observe something like this. Red continues to do worse than green. So against this additional opponent now, red has still done worse. So we have an average in a sense, but we still maintain the ability to compare them, right? There's no need to average or aggregate these things in this case. And that simple observation there led to an algorithm that was dubbed Pareto coevolution because of its connection with multi-objective optimization and the idea of Pareto optimum. And the essential idea there is to do these apples comparisons like I outlined a second ago. And you can think of that as treating the various opponents or the various other entities as dimensions or objectives that individuals are trying to optimize. So the idea being this thing is actually representing an objective in the multi-objective sense, or a dimension, and the task is for these guys to do as well as possible against that. And against that. And so rather than averaging, keep them separate as if they're separate dimensions. And in that case, you produce a vector of outcomes rather than a single number. So here, this is a vector of outcomes, not a single average. And you use this idea of Pareto dominance, borrowed from multi-objective optimization, to do your comparison. So that's the essence of Pareto coevolution. And where I took this was I recognized there was a kind of geometric, this was giving you a kind of geometric view. And in that case then, do you have a question?
You're mapping fitness criteria to a Cartesian space.
I'm sorry.
You're mapping fitness, like if you look at fitness results as a vector, you're mapping those to a Cartesian space. And then finding the relationships therein.
Yeah, that's the idea. Yeah. Yeah, so the idea there is, since the different opponents are acting like dimensions or objectives, why don't you think about this geometrically? And then this notion of informing relates then to this idea of like independent basis vectors in a vector space, or to use the multi-objective optimization lingo, conflicting objectives or dimensions. And I'll have a little cartoon of what that means in a second. But these are kind of well-grounded concepts that you can use to talk about what it means for individuals to be informing or informative. And it also, this idea also suggests a geometric way to think of the overspecialization problem, which is something that Susan Epstein referred to as brittleness, but also appears in other guises, which is that if you do have multiple objectives to optimize, and you focus all your attention on one of them instead of all of them, then in some sense you're over-specializing on that one, and perhaps this brittleness problem is a result of that. So here's just a little picture. Let's say you have this kind of multi-objective space with these two criteria, and I'm just calling them generically F1 and F2. And you have this trade-off surface with these three individuals, R, P, and S. So what this picture is telling you is that against this objective, R is better than P, but against this objective, P is better than R, so there's a kind of trade-off between the two. If you neglect this F2 dimension and think solely of F1, then you get this ordering. It looks to you like S is better than P, which is better than R. And that will give you the erroneous belief that S is actually the best thing that you have. Now, try to step back a second and think of this as a coevolutionary algorithm where these objectives are actually other individuals. If your population only, if your T population only contains this guy and your S population contains these guys, then you'll conclude that S is the best one there. Whereas if the T population only has that guy, you'll conclude that R is the best one there, and so you'll change your mind about who's best. Whereas if you have both of them, you'll see immediately that there's some kind of conflict and that all three of them are somehow equal, or at least different. And so the over-specialization issue can occur when you neglect these additional dimensions. And the idea of informing, or informativeness, would be when you see that individuals are producing dimensions that conflict like this, try to keep them. Don't discard them. So I wanted to, I should say that part of my PhD work was giving a nice formal, theoretical, mathematical grounding to this idea. And I have a series of papers about it. I'm giving you just a cartoon overview of it for lack of time and space and so on. But I've taken this idea and formalized it mathematically and proved a couple theorems about how to decompose the population or a set of individuals into dimensions like this and what those things mean and what it means for them to be in conflict and so on. So I want to say that this isn't just fancy talk. There's a series of papers I could point you to that sort of elaborate this idea mathematically. But what I'd rather do here is talk a little bit more about experiments, because I can show you some demos in that case. And one way that, I've attempted to validate this idea is by comparing a couple different algorithms, a couple different coevolutionary algorithms, and I'm just naming them here, on the same kinds of problems and observing their behavior. So one of them is a Pareto coevolutionary algorithm, and one of them is more like a vanilla coevolutionary algorithm where you do kind of fitness proportional selection and you have a numerical value of fitness versus a vector. And here, I've run these experiments on these abstract test domains that were designed to sort of amplify this over-specialization problem, but also to have some controllable features. So we can control how many actual dimensions the underlying domain has and see if the algorithm is somehow sensitive to those things. So let me tell you a little bit about how the algorithm works, and I'll show you a demo or two. So this population-based Pareto hill climb. Again, we have two populations like so. We make some variance, as before. But the key is that parent and child are compared to one another. So you don't do a selection across the whole population. You only compare these two to one another. And the way that you do it is, you have them both interact with someone here, and they get a value, which is recorded down here. And then they interact with someone else and someone else. And I have all the outcomes recorded like this. And then you do Pareto dominance here. And so in this case, the purple guy is better against all three of these different interactants that all three of them face. So it's better against this one, it's better against this one, and it's better against this one. So in that case, you discard the parent. This is the case when the mutant is better, and you keep this one. And then you repeat for all these other parent-child pairs. So that's the population-based Pareto hill climb. So it's a simple enough algorithm. But let me, it produces a pretty dramatic change in results on these games. Let me tell you what you're seeing in this picture. The abstract games that I'm using have two types of individuals, both of which are pairs of numbers. And so when two of these guys interact, there's a computation that's done on their coordinates, and then it outputs either a 1 or a 0 to say who won. So from the perspective of the algorithm, the only information it gets is the real log. It doesn't see the board. So it's a black box that just says this guy is better than this guy. It doesn't know anything about the dimensionality of the individuals, that they have tuples of numbers. So what you see here are the two populations of the population-based Pareto hill climber. And what you see here is one of the populations of a more ordinary to disproportional coevolutionary algorithm. And what I'm arguing here is that this population has thoroughly over-specialized on this axis. In other words, it's moved quite far down this axis, but it's made very little progress on this one. This algorithm, by contrast, has made a sort of balanced progress on both. So this purple set here is the S population, the ones that are incentive to perform well. And they've more or less made the same amount of progress on both axes. These guys are the other population, the T population, or the ones that were incentive to inform. They, if you can see, have aligned themselves along the axes of this space. And I want to bring that out as somewhat remarkable because the algorithm knew nothing about the axes of this space. I knew it, but the algorithm did not. Nevertheless, these individuals have more or less aligned themselves along the two axes and also have formed in these two clusters corresponding to the axes. So I can control how many axes there are in the game. I've plotted a 2D version, but I can increase that to 3 or 4 or 5, and you maintain the same observation that you get in a 5-dimensional game, you get 5 of these points. In a 2-dimensional game, you get 2 of these points, and some outliers. This guy was first, so
quick question. I get how that works if you're just dealing with I get how this works if you're just dealing with mutation. So red mutates to magenta, you just compare the two.
Yeah.
Now if you're crossbreeding, so you have red and green, who does it compare with?
All right. So there, an algorithm that I've used based on this thing called deterministic clouding by Sandy Mahfoud. This is an algorithm that is very much like a hill climber, but with crossbreeding. So what you do in that case is you have your two parents, you do your crossbreeding and your mutation, and you have the two children. And then there's a pairing function, which is based on some kind of distance metric, often genotypic, that pairs up the offspring with the parent that is closest to the offspring. And then they're paired, and then they're compared, only parent against child. And then you can do a very similar thing with that algorithm, and now you have crossbreeding. So yeah, deterministic clouding is a very nice algorithm.
Doesn't your population size keep growing though? If each one wins some and not all, then you won't be able to eliminate so many.
You have two parents and you produce both recombinations of them. And then you compare this parent to this child, and whoever's better stays and whoever's lost is discarded.
Right, but if each of them wins some of their competitions, then don't they both stay?
No. It's just the offspring is only compared against its nearest parent, and only one of them stays. So you always start with two parents and end up with two survivors. The survivor could be the parent or the offspring, but you always have two going to two. So you can have a fixed population size.
If some win some, and if one wins some and the other one wins some, how do you know which one gets removed?
Well, the comparison is only done between parent and child. It does no other interaction. So there's no win-some.
Aren't they competing against multiple opponents?
I'm sorry?
Aren't they competing against multiple opponents?
Are you referring to deterministic crowding or the algorithm I outlined?
I don't remember.
Yeah, let me back up a bit then. Maybe I messed up. So the idea here is that these guys are being compared with one another and only one of them will survive.
Okay,
right? But they're interacting.
Here, purple won all, right? What if purple didn't win all? What if they each won some?
Yes. So that's a wrinkle that I did not tell you about. So in that case, they would be non-dominated in the Pareto sense, and you need to make some kind of decision. Do you keep them both? Do you discard one? I'm kind of aligning those details for the sake of time. What I do in that case is I maintain a fixed population size. I take the Pareto front. So I discard all the ones who can be discarded. Then I take the Pareto front of what remains, which I guess is going to be the Pareto front, over all these guys, and I chop it down to fit into the population size. And there's some details there.
Which ones you remove?
Yeah. There are a couple different ways to do it. Yeah, it's a bit of a detail. But for this particular algorithm that I'm going to show you, what actually happens in that case is that the child is kept. The child is kept when they're not in a non-dominated case. So the parent is discarded. No, sorry, the parent is kept.
Okay.
Yeah, there's a good reason not to keep the child. That's if they're non-dominated, you should keep the parent. There are some good reasons to do that.
So, Anthony, only when the child strictly dominates the parent, do you replace the parent with the child in this computation?
Sorry?
Only when the child strictly dominates the parent?
Yeah, the only case in which the child is kept is this one, when the child strictly dominates the parent. So even if they're equal, the child is not kept.
And why only compare parent and child? Why not just compare them all against each other within a given population?
You can do that too. So the coevolutionary algorithm, there's a bunch of variants that do it that way. Here I'm using a population Pareto hill climber because it's a very simple algorithm.
So you end up with a different result?
Pardon?
Well, compare all of them, or you compare all the individuals at the end of it. What's the difference?
There is a difference. That maybe is a little bit more detailed than I want to get into at the moment. But the basic idea is that population-based hill climber like this has a kind of implicit diversity maintenance mechanism in it. So it might be that this guy dominates everybody in the entire population, and if all you did was take the Pareto front, you would discard everyone and keep only that. But since it's only being compared against its parent, at worst it can replace this one only, and these guys get a chance to survive. That's the basic reason. It's a kind of implicit diversity mechanism.
What are you using you're doing something similar on the T side as well, right?
Yes.
I didn't quite follow. Are you doing exactly the same?
No. Something very different is happening over here, and I omitted the details because the math's a bit heavy to get into. But the idea is basically that this thing is treated like a dimension or an axis, right? So it's giving numbers to these things. And so you can imagine having all these guys interact with that and plotting it on a number line, right? You can do the same thing with this one or this one. And the question is, if you plot these guys on a number line defined by this, do they go in the same order as this one? And if so, they're not really telling you anything different from the perspective of comparing things. And so they're not informative with respect to one another. You can discard them. That's the basic idea. So I'm not giving you details about how that works here. It's just a bit much to get into at the moment, but I can tell you about it.
Okay. Is this like near multicollinearity and regression? Is this like near multicollinearity and regression? They're effectively telling you nothing additional?
Yes, yeah. You can think of it as an entropy kind of thing. Do they have different entropy? You can think of it as, are they collinear? You can think of it as, there are a bunch of different ways to look at it that are slightly different but more or less the same idea. Yeah. But basically, is this giving you different information about this set of things than this one? That's the bottom line. And however you define information is...
In the ideal case, they're orthogonal.
Yeah, you'd like them to be orthogonal.
Does hill climber have anything to do with conjugate gradient, or can you actually calculate a gradient for hills?
In general, no.
Can you repeat that question?
He asked if this is anything like conjugate gradient or like a gradient descent or ascent algorithm. Because this is an evolutionary algorithm, you're making a random change from this to this. A gradient algorithm would have some kind of directed change. Like this might have a bunch of parameters. Well, it's a stochastic search algorithm. It's like a random heuristic search. You're producing a random variant. You don't, and it's under the assumption that you're working on domains where you can't define a gradient. Like if these are checkers players, what's the gradient? I don't know. How do you take the derivative of a checkers player? Right. So it's applicable to a wider space of domains with the cost that you're making random instead of directed change.
Well, then you take the objective function.
Yeah, but you need to take the derivative of some variables. But what if these don't have numerical parameters? What if these are discrete? They're specified by discrete symbols. There's no derivative. I could have a Lisp program saying checkers. and I can't take the derivative of anything in my list program. Nevertheless, it places it in the checkers, and I would like to find a better one. So you can use an algorithm like this in that case, where you can't use it like gradient descent algorithm. That's kind of the idea. Okay. So where was it? Alright, so here's this picture. This is taken from a paper I wrote in 2004. But what I wanted to do was demo this live, because the picture doesn't show you the dynamics, and I think the dynamics are more interesting. Well, it's live, so I'm not great. Bravery. Well, I already picked the random seeds. Not quite. So, here's a space, and I have some experiments set up. I can't read my own. Where's my map? What happened? I want to drag this over here so I can read it. Right. So let me show you. First of all, I wanted to show you a kind of simple, vanilla, fitness proportional coevolutionary algorithm running on one of these number kind of games. So let me run it a bit, and then I'll pause it and show you what you see. I'll tell you what you see. All right. So what you have here is just like in the graph before. There's a bunch of individuals. I don't know if you can see the colors, but they're red and blue. The blue guys are the S population, the candidate population. The idea is that they want to go up here as far as possible. The individuals up here are best. The red guys are the S or T candidate. And this is using pretty standard so-called simple coevolutionary algorithms, where you have to evaluate a guy in the blue population and have it interact with everyone in the red population, take the average fitness, like I outlined early on, and give it a number, and then you do like a roulette wheel selection of that, and repeat. So they all started somewhere around the origin here, and what you're seeing is that they're sort of clumped on this axis, and I'll start it up again, and what you'll see is that they continue to move along this axis, exhibiting that over-specialization behavior that I talked about, on the previous slide. So there they go. And you can run this a long time, and eventually they're going to hit over here and not get anywhere. And they're actually kind of going slightly down. So if your goal is to have the guys be up here, and you know that these are the best things, that's pretty bad. You really don't want that to happen. So this would be kind of a typical coevolutionary algorithm. You see these published, and yet it's exhibiting this behavior that you really don't like. Where is it? So now I'll show you. Yeah.
If it's purely coevolutionary, how do you know an absolute fitness, upper right?
The domain that I'm not telling you what the domain is this kind of abstract game that we invented. The highest average fitness guys are here if you average across all other possible guys. And also in the Pareto sense, these are Pareto dominant. So we know just by design of this domain that in several different senses the guys up here are best. But according to the algorithm, since it only sees a small subset of that, it can't see that. It can't know what's best. So here's this population Pareto hill climber algorithm on exactly the same problem with the same mutation rate, population size, everything the same. The only thing changed is the selection mechanism. And so you can start to see them clustering the way that the graph previously showed. But I guess what I would like you to observe is that this trend is continuing. I showed you a frozen snapshot in the graph, but these guys continue to be clumped here and here, and these guys continue to move.